Hello, Professor. My name is Harrison Hopkins, and this is my final research project for the AI class at Kennesaw State University for summer of 2019. The topic I decided to go with for my paper was AI and gaming. Being as I am a computer game design and development major at Kennesaw State, I wanted to research something that I was passionate about. AI and gaming is something that I find very exciting because I've kind of grown up with the gaming industry, and I have seen AI grow alongside me. So given this opportunity, I wanted to look into what kind of advancements AI has made and what algorithms are popular in game design today. So I'm going to start this by overviewing the paper that I wrote, and then I'll do a bit more of a presentation for the video. So the first thing here is the paper as written by the guidelines that were posted in D2L under the Content tab, under Syllabus, and within the CS 4242 Online Project Guidelines for Summer 2019. So I have my name, all relevant information, and I started with a brief history of AI in gaming, which explains when it started, what it is, when changes occurred, etc. I then start to analyze the problem of how AI can be difficult to work into games, but how much of a necessity it is, and some issues that programmers have with making AI a asset to their game more than a detriment. I move on to reviewing the literature that I read to learn more about this topic, and each one of these paragraphs has a Here button that will bring you to the website that I actually viewed myself, and a References button that will bring you to my reference page to show where the actual literature that I reviewed is referenced. I move on to the algorithm and application, where I dig into what algorithms I found interesting. One of the ones that I found was FSM, or the finite state machine, and I have a basic graph here. And I dig into that one a little bit, but I focus primarily on the Monte Carlo search tree, or the MCST. I dig into that more on implementation and experimental results, where I look into how the Monte Carlo search tree was utilized, as well as what it does and how game designers have worked it into their games. Moving past that, after that analysis, I look at the advantages and drawbacks of the MCST, focusing on how it, operating as an AI unit inside of games, has both helped games to feel more enjoyable, realistic, and like you're working against a thinking machine, as compared to some of the ways that AI can potentially make it feel or act dumb, for lack of a better word, or not properly, or not make the game any more fulfilling than it is. Finally, I have my summary, where I kind of write about the applications of MCST and some of the discoveries that I made personally along the journey of studying about MCST. And then finally is my reference page. So I have 7 pages of writing, single space is recommended, and an 8th reference page. But instead of reading through this paper for the presentation, I thought it would be a lot easier to look at a PowerPoint. So I decided to make a PowerPoint to help understand this more. So again, my topic is AI in gaming. That is what I decided to go with. And I focused entirely, or mostly, on the Monte Carlo search tree, because it is one of the more popular AI methods or algorithms that is used in gaming today. So the brief history starts with the game Pong, which was released in 1972. That is one of the first noted instances of AI in a game. Now, a rough version of Pong, a sort of tennis-type game, was released on an oscilloscope back closer to the 60s, but that game had no AI. Back then, if you wanted to play, you had to have somebody to play against. Pong was really the first instance of AI, and all it was one of the paddles would move up and down and attempt to knock the ball back at you. So the AI, all it knew was where the ball was and how to move up or down so that the ball collided with it. That was the extent of the Pong AI. Since then, it has grown to enemies that can decide their own thing, and popular video games such as Destiny or Halo, where the enemy understands the scenario of what's happening, when it's being shot at, when it is damaged, when it should hide, when it should attack, etc. As well as AI that Monte Carlo search tree would work most closely with, which is AI in games such as Assassin's Creed, Red Dead Redemption, or the Civilization games that require a lot of understanding scenario and reacting appropriately. So the first problem that I came up with AI is that as it has grown, programmers have really struggled with understanding how it could fit into their games, and have had to work with the potential drawback of AI being a detriment to a game if it was not programmed correctly. The biggest issues here are AIs that are too smart or too dumb, because if an AI is too smart, it could make the player feel like they're not needed in the game, or like the game is impossible to beat. because an AI enemy could prevent a player from being able to complete a task, complete a mission, or complete a fight, or whatever. Or if it's too smart, it could complete all of the work for the player, making the player essentially feel like the game doesn't require them to actually play. On the other hand, if an AI is too dumb, as imaged on the right, you can see that those two AI are attempting to fight a unit, but there is a wall between them. So you essentially lose your AI because all they do is stand there and shoot at a wall. This is actually a reference to an early Halo game. If the AI is too dumb as well and is an enemy, it makes the game feel too easy because you travel through, and if the enemies aren't attacking you or are too poorly designed to attack you with any efficiency, then you'll breeze through the game and you won't feel any of the challenging reward of fighting a difficult enemy. So that's some of the issues with AI. And as mentioned before, it's easy to be bad. And this figure, which is taken from my paper, I actually created this figure myself, starts with AI and explains that if it is underdeveloped, then the enemies are pushovers and too easy, like I stated before, or the computer characters don't have any presence in the game. So if there's supposed to be a really cool character that you're supposed to work with as a companion in a game, but they have an underdeveloped AI, you could start to be more annoyed by their presence than alleviated by them being there. So if you have a dumb AI as an enemy or a companion, the game can start to feel tedious or boring. On the other hand, if the AI is overdeveloped, enemy characters can be too powerful and make the user feel useless. So essentially, either the AI ally, if it's overdeveloped, is doing too much work and is making it hard for the player to feel useful, or the AI overdeveloped enemy is so hard to kill or fight or defeat that the player is feeling like there's no way they'll beat the game and eventually will give up on playing altogether. So this is why it's easy to be bad with AI, and you have to it's a very thin line that you have to draw between too good, too bad. You have to find the middle point. So next up is the literature review, and that's where I read all kinds of things. My primary source was actually a paper written by a college graduate. There was a Harvard blog post that explained a lot about the history of AI and actually introduced me to the Monte Carlo search tree. And then there was a master thesis on AI that helped explain how it was utilized in strategy games for decision-making purposes. And that was actually that's actually one of the primary uses of the Monte Carlo search tree. So the first algorithm that I found was finite state machine, and this was the figure on the side is one that I took from one of my sources. It's listed in the paper. And what the finite state machine does is essentially understands what's happening and makes a move based entirely on that. So a programmer will generalize all the possible situations that an AI could be put up against. So in this, a sword fighting game. So the enemy AI will wander around until it sees a player. If it sees a player, they will immediately switch into attack mode. If the player starts attacking, they will attempt to evade. If the player attacks them and they lose health, they will immediately run off and attempt to find health to heal themselves. And then once they're healed, they will immediately switch back into attack mode. This essentially understands what's happening and chooses an immediate course of action, diving straight from action into action. There is no thought about it. It's an immediate segue from action to action. So I thought that was interesting, but I didn't think that it was quite as AI as I wanted it to be. So then I found the Monte Carlo search tree and how that works. The graph or the figure on the right side of the screen is about the Monte Carlo search tree, and what it does is it understands all of what's happening in the game. It perceives the game world around it and what's being implemented by the player or other AI, and then it is past all of its potential moves by the programmer, so it understands which moves are available to it at any given time. It will then, much like the A-star algorithm, look at each one of the potential nodes or one of the potential actions it can take, weigh the payback value of taking that action against all the other potential actions. So, and then find the path that would provide the highest reward. So if you look over here, you'll see the initial state is the player is attacking an AI city. So we're assuming that this is a game like Civilizations where each person has a city and you can attack, defend, or build. So the player is attacking the AI city. The AI can either defend, build more technology, or attack in return. So it checks each one of those nodes for the payback value, which is demonstrated here, red being a high payback, low being white. And it'll check each one of these nodes to identify the best action. So in this, it determines that attacking the player is the best course of action and moves down that tree, again, iterating through each one of these nodes, deciding which one of the actions would return the most payback. Now, assuming that it attacks, the player decides to retreat, the AI will notice this and then immediately alter its course of action for the newest high payback. So if it attacks and the player retreats, it might decide that building technology is the next highest payback. So it'll immediately switch to a different node and start iterating once again, looking for the path of highest payback. Much like the A-star algorithm that we learned about earlier, searches through things and looks for whichever has the lowest weight or the lowest cost to get from point A to point B. So too will the Monte Carlo search tree look at all of its options, weigh them, measure their benefits against one another comparatively, and then choose the course of highest returns. So this can also be edited by programmers to be smarter or slower. So if an AI is thinking too quickly and deciding paths too rationally, you can slow down how it makes this decision-making process, and that's kind of a good way to judge AI difficulty in a game. So the drawbacks to the Monte Carlo search tree are that although it allows the AI to think for itself, you can make an AI too aware. Considering you have to program the AI's knowledge of in-game activities, if you allow them too much knowledge of what's happening in the game, they can start to perceive events that they aren't supposed to perceive. So if the player was building an army, the AI could perceive that it was building an army before the player revealed that fact and start countering before the player even attempts to do anything. This would make a impossible to defeat AI, making the game no fun. Alternatively, if you restrict the AI's access to information too much, it won't understand what it's supposed to do. So it could get attacked by a player, and instead of choosing to retaliate or defend, it could decide that it should just start building things, or not understand that it's getting attacked and do nothing. So you really have to balance with the MCST how much information is given and what it decides to do with that information to keep the AI from being either too powerful or too weak, so that your game has a good feeling to it and good replayability. The big advantages of this are that by making AI opponents which can act in unpredictable ways, whose behaviors are not hard-coded or predetermined, you create a lot of joy in your game. A player can go in, play against an AI unit, and have a varying experience every time. You could play against an AI 10 times, and each 10 of those matches would be different because the AI is deciding what it should do as it's playing instead of being predetermined by hard code. Another thing is that it's great for managing gaming ecosystems or planets or anything, because that allows them to use them on basic versions of MCST and plugging them onto simple things like birds or bugs or animals. And those animals, instead of being hard programmed to walk through the world in a set way, which looks repetitious and robotic, the creatures would iterate through their surroundings and make changes to their pathing or the way they act to certain noises or certain actions based on the search tree. Again, adding that realistic, thoughtful appearance to each one of those creatures. So Monte Carlo search tree is really good for creating a sense of realism in environments. In summary, the Monte Carlo search tree is great. I know that's kind of a general thing to say, but because of it, we have been able to gather all kinds of different AI and create worlds that feel a lot more alive and populated, as compared to some early games where you run through the streets and there's one person who is hard programmed to walk back and forth and say hello if you talk to them, or an AI that stands on a street corner and talks on their cell phone endlessly. You're provided the option to have AI that feels alive, that acts on its own, that responds to the situations around it, making a game feel much more enveloping, making it a lot easier to dive into the game and be wrapped up in what's happening. And some examples of that are games like Hitman, which is listed on the top picture. And Hitman, most levels have 150 to 300 AI-based characters, some of them more basic than others, but there are several types that will walk around, they'll stop to go to the bathroom, they'll go get a drink, they'll walk into the hallway to make a cell phone call, and all of those can be interacted with, and they react to strange behavior, to acts of violence, to loud noises. So each one of the AI reacts very real, so as you're playing the game, you have to understand not to act too strangely because you will be recognized. Alternatively, There's games like Assassin's Creed and Red Dead Redemption 2. Assassin's Creed is much the same, where the cities are filled with people who go about their daily lives, shopping at the market, walking to and from their house, walking to general public areas, and each of which can be interacted with and get suspicious of you if you act strange. And Red Dead Redemption 2 is actually a newer game and is filled to the brim. It's a very large open world with animals that roam around, alligators that crawl through swamps. You'll have birds that fly and roost with day and night cycles. You have people who ride their horses to and from towns and freak out if there are loud noises. So if you were to fire a gun off by a horse, the horse would react by jumping and running away from you. And this is all thanks to things like the Monte Carlo search tree, where everything is pre-programmed to understand if something happens, what are my responses to that? And it chooses the best response for whatever that AI is designed to do. So learning about the Monte Carlo search tree was actually very enlightening, because I can kind of understand how these big AAA title creating companies program their AI to not only think but act realistically and respond to situations. So when you boil right down to it, it is essentially a search tree. But it's a search tree that utilizes a method much like A*STAR that weighs the values of every potential action that can be taken, and then finds the best one, as most things in real life would do. Think about what they're about to do and choose the option that they believe is the best for whatever scenario is handed to them. After doing all that research, I thought very much that that Monte Carlo search tree was a very good thing. I was happy to learn about it. It was fun to write all the research about it and to read kind of about how games were developed and started growing. I'm excited to see this continue to grow as computers and good processors become more and more available. I am looking forward to larger AI in games, and I'm excited to see the eventuality of having a fully functional autonomous planet where the birds, the bees, the grass, the trees, and everything understands how to react based on the situations around it. And as we continue to progress more technologically, I do believe that that's something we're coming close to. So, again, this has been Harrison Hopkins with Kennesaw State University's AI class of summer 2019, and this was my final research paper and presentation. Thank you so much, Professor.